Hello, my dear students. How are you? Hope you are quite well. And without wasting time, I just want to say that today we are going to discuss on the RS nomenclature. RS nomenclature of what? Simply RS nomenclature of organic compounds. Okay, so I am not going to discuss the theories, the points, the notes. Okay, so these are not purely not asked in the questions in the exams. Okay, you will be given some molecules, some organic molecules, and you will be asked to write their names with R and S nomenclature. Okay, so let's start. So if uh, first two terms you are to remember, two terms, that is flying wedge, flying wedge. Okay, so flying wedge and Fischer projection, these are the projections, flying wedge projections and Fischer projections. Fischer projections. So basically these two are for applicable for organic molecules, organic molecules, for the organic molecules. Okay, so when it is applied, when structure of any organic molecule is determined. So basically when you are to determine the structures of the organic molecules, then you might encounter with these two terms, that is flying wedge projection and Fischer projection. So why we are discussing flying wedge projection or Fischer projection, but our topic is RS nomenclature? Because if you don't know how to write the Fischer projection for, structures and flying wedge projection structures of organic molecule, then you may not understand the RS nomenclature of the organic compounds. Okay, so before going through the RS nomenclature, you must know what is the flying wedge projection formula, what is the Fischer projection formula, and how to interconvert these, that is from flying wedge to Fischer, that is from flying wedge to Fischer, and from Fischer to flying wedge. This interconversion you should know. Okay, so let's start. So if a molecule is here, C COOH H OH, and here CH3. Okay, my dear students, so this is what is the name of this compound? This is lactic acid. This is the lactic acid. This is the lactic acid. So this formula is this and basically this is written as in your exam, in your question paper or your books. This is written as CH3HOH. This is the Fischer projection formula. Fischer. Okay, so where the carbon gone? The carbon basically the vertical line and the horizontal line. This is the vertical line, and this is the horizontal line. So where the vertical line and horizontal line meets each other, that is the junction point, here the carbon atom situated. Okay, so this is the carbon atom. So where the carbon atom situated? The carbon atom situated on the point where vertical line and horizontal line in Fischer projection formula bisects. Okay, so and remember, what is the type of carbon atom? The four bonds, that is the OH, this is the COOH, this is the hydrogen, this is the CH3. So if you write here 1, 2, 3, 4, then you can see 1 not equals to 2, not equals to 3, not equals to 4. That means the four groups or four moieties or four atoms, the four groups 1, 2, 3, 4, the four groups attached with this carbon atom all are different. All are different. So this carbon atom, this asteric carbon atom, this carbon atom is attached with four different types of bonds. That's why this carbon atom is called chiral carbon. Okay, this carbon atom is called chiral carbon. So this is called chiral. Why this is chiral carbon? Why? Because the this carbon atom, this carbon atom is attached with four different types of bonds. Four different types of bonds. Maybe better it is written as four different types of groups or atoms. Four different types of groups or atoms. So this is the chiral carbon. So when you are going to derive the RS nomenclature, basically the R and S is based on the whole molecule. Okay, and the R and S basically determine the optical property of the molecule, and that optical property of the molecule in turn optical property of the molecule in turn depends on the chiral carbon. So I repeat, the R and S nomenclature, R and S, mind it. Okay, the R and S nomenclature of the organic compounds is applicable for the whole compound, whole molecule, not for any specific atom in the molecule. But RNA's nomenclature, RNA's designation is applicable for the whole molecule. And it, that is RNA's nomenclature, signifies optical property of the molecule. And that optical property of the molecule in turn depends on the chiral carbon center. That is, whether chiral carbon is present or not. In lactic acid, you can easily see that chiral carbon is present. Okay, my dear student, I think you are well understood. So next, so what we are doing? We are doing the Fischer projection formula. So this is the Fischer projection formula. So Fischer projection formula is basically, this is the Fischer projection formula. Fischer projection formula, that is, it is easily seen that all the groups, that is the carbon atom, this carbon atom, COOH, OH, CH3, hydrogen, all are written on a plane of the paper. That is, Fischer projection formula is a two-dimensional structure or projection. Fischer projection is the two-dimensional projection, because in Fischer projection all the atoms are written on the plane of the paper. Okay, so this is the two-dimensional representation. It is the two-dimensional representation. Okay, and the vertical line and the horizontal line lies on the plane of paper, on the plane of paper, on the plane of paper. Okay, so now how to write flying wedge from the Fischer projection. So next topic is the flying wedge. So our next topic is the flying wedge. So how to interconvert Fischer projection to flying wedge? So what is the flying wedge? Wedge means what is the meaning of wedge? So you should going through your dictionary to know what is wedge. So basically the flying wedge formula is a three-dimensional projection. It is a three-dimensional projection. Number two, the vertical line, the groups on the vertical line, the groups on the vertical line, the group on the vertical line of what? This is vertical line of Fischer projection formula. Vertical line of Fischer projection formula lie on the plane of paper, plane of paper, plane of paper in FW. FW means flying wedge. You can write the points. You can write the points by pausing the video. I think the video is quite visible and my sound is also audible. If you are facing any problem to visualize the whiteboard and uh, and to my sounds and volume, you can write in the comment section. I think the volume is quite audible. If it is not audible, you can write in the comment section. So the groups on the vertical line of Fischer projection formula lie on the plane of the paper in flying wedge formula. Now what about the horizontal line? The horizontal line, number 3, the groups in horizontal line in Fischer projection lie above and above the plane. Above the plane is written as the bold wedge. This is the solid wedge or bold wedge. Lie above the plane. Sorry, lie above the plane of paper in flying wedge and below, and the below the plane of the paper here written as the dashed wedge, and below the plane of paper in flying wedge. Okay, so you can see that here. So the flying wedge structure, what will be the flying wedge structure of this? So here the carbon, here the chiral carbon, here the chiral carbon which is not clearly written in the Fischer projection. You should write the chiral carbon first in flying wedge. What we are going to do? We are going to do the structure of the lactic acid, this structure, this Fischer projection structure of the lactic acid, to interconvert it in the flying wedge projection. So this is the carbon. What carbon? This is this carbon atom. Okay. So the COOH group and the CH3 group, the vertical line containing the COOH and CH3 lie on the same plane of the paper which contains the chiral carbon in the flying wedge. So here the COOH and here the CH3. Now my question is, in which side CH3 bent? That is the bottom of the vertical line is the main point of discussion. The bottom of this vertical line is the main point of discussion. Why? Because if you bend CH3 on the right hand side, I bend CH3 on the right hand side. Which CH3? I repeat, which CH3? The CH3 group lies in the bottom of the vertical line, in the bottom of the vertical line in the Fischer projection. We are not bothered about the top group of the vertical line, that is COOH group. We are not bothered. We are taking into account the position of the bottom group in the vertical line. So which is the bottom group of the vertical line? So horizontal line and vertical line are applicable only for Fischer projection. So vertical line bottom CH3. So I bent the CH3 on the right side. I bent the CH3 on the right side, this side. Okay. So if you bend this CH3 on this side, then then now you bend the CH3 on the right side. Right side. So this is the, actually basically if you take this, so this is left side, means this side, left side. So this is bent on the left side. Then now come to the vertical line. This is the bottom CH3 group and this is the top COOH group. So COOH group, this carbon atom and this CH3. I remember this COOH, C and CH3. These three atom lies in the same plane of the paper. This is the plane of the paper. So this is the plane of paper. This is the plane of paper. So plane of paper contains COOH group, chiral carbon and CH3. That is the vertical group of Fischer projection, and the carbon atom, chiral carbon atom. Okay. So now we are what we said, that we are not bothered about the top group but bothered about the bottom CH3. Okay. So we bend CH3 from the left. Now come to the horizontal line H and OH. Okay. So H present in the left hand side, that is this side. H present in the left. This is left and this is right. This is left and this is right, and you bent it left. CH3 bent it left, and here the point 3 we written, the groups in the horizontal line in the Fischer projection lie above the plane and below the plane. So which is above the plane? So hydrogen and OH. Among hydrogen and OH, one will be above the plane and another will be below the plane. So which is above the plane and which is below the plane? Okay. So I bent CH3 in the left. So here left position, that is hydrogen, will be above the plane. So this is solid line. This is the above the plane hydrogen, and rest is OH. It should be below the plane. Below the plane is being represented by the dashed OH. This is the solid OH. This is the dashed OH. Okay, my dear student. So we are going to discuss some other example. So now we can write this here COOH. Now you say that, sir, I will bend CH3 right. Now you can bend CH3 right. You bend CH3 right. So what is the right side of the vertical line? Sorry, of the horizontal line, OH. So OH group will be above the plane, and rest is hydrogen. This should be below the plane. This is the fundamental things. Okay, so COOH, C and CH3. These three groups remains in the plane of the paper, and the OH group lies above the plane of the paper, and hydrogen lies below the plane of the paper. Okay, my dear student. So another example. So this is the Mandelic acid, C, pH, hydrogen, and this is OH. So this is here in place of CH3, here it is pH, that is phenyl benzene ring. So this is called Mandelic acid. Mandelic acid. This is Mandelic acid. So this is the, again this is the Fischer projection formula. Mandelic acid. This is the Fischer projection formula. Now we are going to write its flying wedge structure. So COOH, what is the vertical line? Vertical line. This is the vertical line. This is the vertical line. This is the horizontal line, and this is the horizontal line. So this is the top, and this is bottom, and this is right in terms of vertical horizontal line, and this is left. So in Fischer projection formula, all these things are here, and in flying wedge formula, so this is Fischer projection formula, and in flying wedge we are going to write here the flying wedge. Okay, my dear students. So in flying wedge formula, the COOH, this carbon atom, chiral carbon atom, and the pH remain in the same plane. So we are taking into consideration the bottom. So I bend this pH group here. That is, if this is the line, so bend the pH group at the left. So which atom or groups are in the left position in the horizontal line? OH. So OH group should be above the plane. OH group should be above the plane, and which atom would be right? H. So this should be below the plane. You can write here. And if you think, sir, I will bend the pH right hand side, then which is the right hand side? Hydrogen. So hydrogen will be above the plane. That means the side in which you bend the bottom group in Fischer projection, at that similar side in the Fischer projection will be above the plane. So here I bent pH right side, and which atom in the right side in Fischer projection of horizontal line? Hydrogen. So hydrogen atom will be on the above the plane for flying wedge structure. So rest is OH. So OH should be one position is vacant only, and this is the below the plane. Plane of which? Plane of the COOH, C and pH. That is the plane of the paper. So my dear students, I think you understand little bit out of this class. So you will try. I am going to homework. So I am going to do some going to give some homework now. In your you should try this. COOH, pH, OH. So try to convert this in flying wedge. So my dear student, I must stop here. In our next class, we'll see actually the RS nomenclature. So this is the pre-concept related to the RS nomenclature. If you don't know how to write down Fisher projection and how to write down the flying wedge, you cannot derive the RS nomenclature actually. So I tried something to make some insight of Fisher projection formula and flying wedge formula. So my dear student, keep watching in our next class of part 2 of RS nomenclature, where we are going to do specifically the R and S term, R and S nomenclature, how to derive in S nomenclature. So this is the pre-class. So I hope you enjoyed. Keep watching.